Welcome back. I hope you are doing great. As a part of the previous lectures of this section, we understood different joins, right from inner joins until the semi join, which can also be called as a left semi join and left anti join. Now that we understood how the joins work, as a part of this lecture, we'll understand joins strategies in PySpark. By the way, why do we really need to know join strategies? When we do the joins as a part of the any SQL or RDBMS databases, we don't really worry about the strategies. But why do we really need to worry about the strategies when we do a joins in Spark? Any idea? So to understand that, let us spend a couple of minutes there. If I ask you a question, which is a very super simple question, how is the data stored when we say we are storing a big data? I know you would be wondering such a simple question. The data is stored in a distributed manner. If you have a data like one file GB of the data, the moment we say big data, it will be distributed. We have already discussed this multiple times. So the data is distributed in different systems. In case of Spark, we can say the executors is the place where the data is distributed. We have already understood the joins. How many data frames do you think we need to perform the joins? Such a simple question again, right? We do definitely need two data frames, data frame 1 and data frame 2. So now that we established very simple aspects, first thing is the data is not stored at one place. When we say we are storing a big data, it will be distributed across different systems. And coming to the joins, we have already practiced so many joins so far. In all the joins, we do require two data frames. These two data frames, how do you think they are stored? Very simple. They are not stored in one place. Assuming that we have almost 3 executors here, these data frames are partitioned and stored in a different executors. Assuming that this part of the data frame 1 is stored in executor 1 or taken care by executor 1, and this part of the data frame 2 is taken care by the executor 1, so on and so forth. So this partition 2 of the data frame 1 is taken care by the executor 2, and the partition 2 of data frame 2 is also is there as a part of the executor 2. The point here is, first of all, when we say big data, the data is not at one place. We would need two data frames to perform the joins. Those two data frames are not at one place. You know, when we perform the joins, a particular key would be compared with the another key in different table, another data frame. So if we were to perform a join on big two data frames which is distributed, then we need to really think about the communication strategy or join strategies. That is the reason we are discussing how exactly Spark performs the joins, because the data is not at one place, the data is distributed and we need two data frames. Both the data frames are distributed in different systems. Now that we understood, Yes, we definitely need to know about the join strategies. If I ask you a question, what kind of tables or data frames would be there in any data engineering project which we are going to be part of? Simple, right? Either we would have a big table or small table. So big table or small table. We are going to combine either big table with the small table or big table with the big table only or small table with the small table only. These are the different combinations which are possible whenever we want to join two data frames or two tables as a part of the Spark, isn't it? Now, here, when we understood that whenever we want to join two data frames, we may have big table to big table, small table to small table, or big table to small table. We need to understand how the Spark does this communication between the different partitions of the data in different executors. Broadly, communication is done in two different ways during the joins. One is shuffle join, second one is broadcast join. As you see, as a part of the shuffle join, we can see the data in the partitions are exchanged between the executors, because the keys wouldn't be there in the same executor. The keys would be in a different executors. As you know, when we are to join, we will bring the record of one data frame with the record of another data frame based on the matching keys. So keys will not be there in the same place. It may be there here. So obviously this need to be brought here. Whenever there is a shuffle join, obviously there will be shuffle of data between the executors. And coming to the broadcast join, the data in a data frame would be broadcasted to the different executors. We'll see that in a bit. Moving forward, when we join a big table to another big table, we end up with a shuffle join. As I already indicated, the key here may have a matching key here. So obviously this need to be transferred to here, because we will be combining the record of the data frame 1 with the data frame 2 based on the key. As we have seen in shuffle join, every node talks to every other node and they share the data according to which node has a certain key or set of keys, which we already discussed. Whenever shuffle joins happen, they are expensive. Why are they expensive? Because the data exchange is happening between the different systems, different executors. Whenever data exchange is happening between the different systems, that will kind of choke the network and the traffic will become congested. And whenever there is a problem or whenever the data is not partitioned well, the problem would be much more. So when do we need to join the big table with the another big table? Assume we have a company. In that company, it is receiving a billions of message every day from the IoT devices. So on a daily basis, they are receiving the billions of messages. And the requirement is they want to identify day over day changes that have occurred. That is when there is a need for joining the big table with the another big table. That is when mostly it will end up in shuffle join. Now that we understood how the big table with the big table is joined, What may be a possibility of the join there? Whenever we have to join a big table with a small table, any idea if there is any optimization possible here? Yes, there is a optimization possibility here. What we can do is, if the small table is small enough to fit into the memory, then what we can do is we can broadcast that. We can use a broadcast join there. So what essentially happens as a part of the broadcast join is, the small table, whatever you have, that will be broadcasted to all the executors. Assume this is a small table and this is one executor 1, this is executor 2. Now this data frame has to be joined with this data frame. So this is one partition of the data frame 2. This is another partition of the data frame 2. So this is the table in entirety of data frame 1. This is the data frame 1. Since this data frame is small enough to fit into the memory of this executor, this will be sent, or this will be broadcasted from the driver to all the executors. So that way there is no need of data exchange here, because whatever the records of the data frame 1 need to be joined with the data frame 2, that will be there here only. Of course the data frame 2 is partition, but that doesn't matter, because all the records of this can be easily compared and joined with the data frame 1. The same is the case here. I hope you are getting this point. Even though this sounds expensive, that broadcasting of the table from a driver to executor may take some time, but once this is broadcasted, in a way it prevents us from performing all to all communication during the entire join process. So we perform this whole broadcasting only at the beginning, and once it is broadcasted, what is happening is, individual worker node is performing the join without having to wait or communicating with any other worker node. But in case of shuffle join, it has to wait, because the data is exchanging between the two different or many executors. So at the beginning of the broadcast join, there'll be a large communication like the shuffle join only. But immediately after that congestion of the traffic, there'll be no further communication between the nodes. Okay, that means joins will be performed in every single node individually. So whenever there is a big table and a small table which can fit into the memory with enough breathing space, we can go for a broadcast join or broadcast communication strategy. Those are the two important strategies or communication modes in a Spark. But those would be classified into different strategies. Some of the important strategies are broadcast hash join, shuffle hash join, shuffle sort merge join. This one is a default in PySpark. So whenever you perform the joins between the two data frames, more or less this will be there. And there are other strategies also depending upon what you are doing, like broadcast nested loop join is there, Cartesian join is there. So what you got to understand at a basic level is, whenever the joins are done, the joins will have a strategy at a high level. It can be a broadcast, it can be shuffle, but those are further broken down into broadcast hash join, shuffle hash join, shuffle sort merge join, broadcast nested loop join, Cartesian join. We will be seeing all these things in detail as a part of our PySpark advanced course. But for now, you just need to understand how the broadcast join happens, how the shuffle join happens. But now that we know there are different join strategies are there, do we really need to choose the communication strategy? Usually, Apache Spark internally chooses the best join algorithm or strategy. Whenever you are performing the joins, when you don't specify or when you don't hint that you should be doing this particular join, Spark is internally choosing whether you should go for a shuffle sort join, what kind of a join it has to perform. Okay, but if you really want to control what is happening, what kind of a join happening, what you can do is you can influence the decision by using the hints or options. So when you specify the hint in the join syntax, the developer is asking the Spark to do something that it otherwise would not do. So you got to be extra cautious whenever you are hinting the Spark to perform a particular communication strategy. If you are thorough, then only you got to do that. If you really know what kind of a join, what are the different aspects of the joins, how it need to be implemented, then only please go ahead and hint. Otherwise, that may lead to the out of memory errors, or you may end up in system crash or something like that, because you are not dealing with the small amount of data here, you are dealing with the big data. On the other hand, if the developer is really good in this whole strategy, it is always better to specify the strategy to optimize the join operation. Wonderful. We understood different join strategies in Spark joins at a very high level. Thank you. You have a wonderful time.